Okay. So this is the theorem that we're going to work through right now. Every non-empty set of natural numbers has a least element. And this is something that we talked through 26. We just stated it out loud right before the break. But yeah, this theorem seems pretty obvious, but we'll talk after we work through the proof about systems where this law fails. And it fails in some surprising number systems that you might not think it would fail in. Number systems that we use every day. Okay, so the proof of this is challenging, but it's very, very pretty. And someone asked, what do you mean pretty? And to that I'd say something to the effect of, it's pretty in the same way that music is pretty. It just is. You just look at it and you say, wow, that's just really nice. So it's yeah, I think just like a Jackson Pollock painting, like so. All right, so let's consider, yeah, I can tell. So let's consider n to be the set in question. So n is any non-empty set of natural numbers, right? Yeah, because it says every non-empty set of natural numbers. So that's the set that we're talking about. Okay. And so what we're going to do, this is a very tricky definition for M. Okay, now M, we usually think of it as something that we use for induction. Here we're going to use it to show that induction doesn't hold. Okay, that may sound confusing right now, but it's not that confusing. Once you see it, you'll be fine. So let M be the set of natural numbers such that M is less than or equal to n for all elements of n.
For all n elements n?
Mm-hmm. So n is just a element of that set, right? So any non-empty set of natural numbers. So that's our capital N. Now you pick any element from that set. We're going to let M be all the numbers that are less than all of those n. Right? Let's yeah. Yep. Yeah, let's do some numbers here. So let's let n be this set here. Let's suppose we had 5, 7, 10, 13, and 19. Any non-empty set of natural numbers has a least element. What is it in this case? 5, right? So that's all that this theorem says. It says pick up any set of natural numbers that you want. It'll have a smallest element, okay? So what M is the set of all numbers that are smaller or equal to all of these. Okay, so what would M be in this case? Well, 1 is smaller than or equal to all those. 2 is, 3 is, 4 is, and, yeah, because we're only looking at naturals. So are we done, or is there another element? Is 5 in there? You guys tell me. Yes. Yeah. 5 is in there. Okay. Let's do another, just for fun. Okay. No. The proof is much more technical. Okay. What if we had the set n equal to, I don't know, 7, 2, 6, 9, and 15? M is 1 and 2. That's right. It's the set of all natural numbers that are smaller than or equal to all the items in n. Right? 1 is smaller than or equal to all those, and 2 is smaller than or equal to all those. So that's it. You have any non-empty set of naturals, and you let m be all the numbers that are smaller than or equal to all the elements of n. So we actually don't even know if that's like a well-defined set, right? For all we know, you might pick up a set of natural numbers, and couldn't this set theoretically be empty? Yeah, it seems like theoretically, can you always guarantee that m will have a number in it? It may not be clear that you can always guarantee that it has something in there, right? But we proved something in the last session. What was it? Theorem 20... I can do this. Where is it? There we go, 24. Theorem 24. One is less than or equal to x, no matter what x is. Okay. So what we notice is that by theorem 24, m will always include 1. Yep. Okay. That's right. It always has 1 in there. And it could have others, right? Here we had m is everything up to 5, but we at least know it always has 1 in there, so it's always non-empty. No, because in the statement we say, pick up a non-empty set of natural numbers. So n is always assumed to be non-empty. Okay. So, all right, good. The question now becomes, all right, we know that m is never going to be empty, but could you ever have a case where it's all naturals? And just based on these two examples that we've seen, what do you guys think? You've got this set of naturals that it's guaranteed to have some items in it, right? So if you pick up some set of natural numbers, could it be that m, which is the set of all numbers that are less than or equal to the smallest one here, could it be that this is all naturals? You say no? Okay. And who's on board? Who says no?
Just by those two examples there? Is that what you're talking about?
Yeah, like based on what we've learned from these two examples, could m perhaps be all naturals?
Only if n was all naturals, right?
In that case, m would be 1. Because you want, yeah, it's the smallest thing, right? You want it to be smaller than or equal to all things from n. Right, but there is none,
Yeah.
right? So there's no last one. So yeah, so
There could be on that.
nope.
What about now?
Because there is no end and it's going forever.
Yeah. So you know, if n has a number in it, this is the argument. And once you see this argument, it's going to make perfect sense. It's crazy. But when you're looking at it, it may be kind of fuzzy, like, I don't know, maybe, maybe not. Once you see this argument, you'll be like, okay, guaranteed, m cannot be all naturals. Okay, so here we go. Very simple. Let y in n. Not m. N. Okay? Where, yeah, we know that there's something in there because we said let n be non-empty, right? Then take a look. We notice that y is strictly less than y plus 1. And so y plus 1 could not be in M. Because M is the set of all numbers that are smaller than or equal to all the items from N. But take a look, pick up any element from N, consider its successor, that thing's going to be larger than an element from N. So it can't be one of the ones that's smaller than all the elements from N. Okay, because M is a set of all numbers that are smaller than or equal to all numbers from N. But if you pick up an item from N, consider its successor. The successor is now larger than an item from N, so it's not in M. So once you see the argument, it's like, okay, that does it. M cannot be all naturals. Okay. So what we notice is that there's got to be some element in M where the successor fails to be in M. And I haven't explained the reason why yet, so if you're confused why that has to be true, I'll explain it in just a second. Okay. So this is why this is guaranteed to exist. Okay. We've already demonstrated that M cannot be all naturals. All right, because if you pick up an element from N and take its successor, you get an element that's not in M. So we know M is not all naturals. But 1 is in M. We've showed that already. by axiom 5, if all successors were also in M, M would be all naturals. Because axiom 5 says if 1 is in there, and if all successors are in there, then M is all naturals, right? But we've showed that M can't be all naturals. So what that tells you is that it must be the case that M successor is not in M for some M, right? Okay. All right, so we're closing in on this thing. What we're going to do is if M successor is not in M, which we've now verified that there is some M where we can pick it up, where we take its successor and it doesn't land back in M. So if that thing has a property that when you take its successor you don't land back in M, then what that means is that M successor is greater than N1 for some element of N. And this all goes back to the definition of M. M says take all the numbers that are smaller than or equal to all the items of N, right? So if this thing fails, what that says is that this is not a number where it's going to be smaller than or equal to all elements of N. In other words, it's going to be a number where that successor is actually greater than one of the numbers from N. Okay? So we pick up that number where this thing fails. Okay? N1 is the number where when you take the successor of M, it's no longer smaller than or equal to that element of N. It's actually greater than it. Okay? But you'll recall that M was in M, and so that means that M is less than or equal to N1. Right, because the definition of M says pick up all the numbers that are smaller than or equal to all elements of N. We know the successor is larger, and so what that tells us is that M either has to be smaller than or equal to N1. And so what that means, it means one of two relations must hold. Either M is less than N1 or M is equal to N1. And we're just going to take these two cases in turn. Okay, this is just by definition of what M was. M is a number in M, capital M. That means it's either smaller than all elements of N, or it's equal to the elements of n. And so this is just a statement of what those elements m represent, right? And we're going to eliminate this as a possibility. Okay? So we're going to consider the m less than n1 scenario. What does this mean? It says n1 is equal to m plus u for some number u. But m was that number whose successor is greater than a number from n. So m's successor was greater than n1. And so what we have is that m plus 1 must be greater than n1. And so what do we have? So we recall n1 is equal to m plus u. And this thing has to be smaller than m plus 1. And this is nonsense, okay, because u is at least 1. And so what this says is that m plus 1 is greater than m plus 1, which is nonsense. Or even worse, it could say m plus 1 is greater than m plus 2. Or it could say m plus 1 is greater than m plus 5. No matter what u value you plug into this is nonsense, right? Anytime you get nonsense like this, that tells you that one of your assumptions had to be wrong. And the assumption was, we said, could it be that m is less than n1? And the answer is no, because if you assume that m is less than n1, you get nonsense. That says this case is out, right? That case is out. Therefore, that has to be the true relation between m and n1. Therefore, since m was in M, we know that M is less than or equal to N for all elements of N. But M is also equal to N1. And therefore, N1, just by substitution here, must be less than or equal to N for all N in N. That was, I mean, I know, I can see everyone's pretty confused. Yes. That is a beautiful, beautiful proof. Yes. That is a beautiful proof. Okay. Yeah. No, I'm glad you asked. So N1. No, I could tell. I just wanted to get through the proof so that we have it on video, and you guys can go review as much of this as you want to. But all that it boils down to that same example that we had at the beginning, right? Where we said, okay, give me, a collection of natural numbers. Let's start with a new random collection, okay? So n's going to be, let's do 7, 12, 9, 6, and 57, okay? Give me a set of natural numbers. Then all that this proof boiled down to is it said, we know there's going to be an m that has the property that, first of all, it's not going to be empty. There's going to be a 1 in there, right? It's going to be 1 through 6, yeah. So m is going to be all the numbers that are smaller than or equal to all the numbers from here. So in this particular example, we can construct it by hand. 4, 5, 6. This is the set m, right? Part of the proof said this is not going to keep going forever. You're going to reach a point where that m terminates and you have a finite list of numbers, guaranteed. So that was part of the proof, is to make sure that you're always going to stop somewhere, right? But now that we know that you stop somewhere, this is all that the proof says. It says, pick up one of the elements from m. There's going to be a special one in there. And when you pick up that certain special element from m, its successor is going to be larger than an element from n. Okay, so let's try a couple. Suppose we pick up 3. Is 3 successor larger than any element from here? No, right? So let's try a different one. 5. Is 5 successor larger than any element from there? No. What about this one, 6? Is 6 larger than any element in there? Sorry, the successor to 6. Okay, yeah, we're looking at successors, right? The successor to this, it happens to be larger than one of these numbers. Right? It's larger than 6. Right? So the set m, the little m that we're talking about as we're going through this part of the proof here, it says the letter m is going to be that number for which, when you take a successor of m, you end up larger than one of the items from n. And that's guaranteed to exist. Okay, we worked through that in the proof. So you're guaranteed to find some element in this list where when you take the successor, it'll be larger than an element from m. In our case, we checked 3. The successor to 3 is 4. Is 4 larger than any of these? No. So we checked another one. Successor to this is 6. Is 6 larger than any? No. But the successor to this one is 7. Is 7 larger than any element from that list n? It is. It's larger than 6, right? So that's what m is. It says, find the element from this list m such that the successor is larger than an element from n. And that's guaranteed to exist. Okay? That's what we were doing here. Is we said, I guess we're doing it on this board. How did the argument run? We said, no. That was just saying that list had to be finite. That m had to be finite. And now, once we know that list is finite, what was the argument to verify that we had one of these? We said, yeah, it's related to that, actually. We said 1 is in m, and if all successors were in m, then m would be all naturals. But we know that it's not all naturals, so that means that there must be some m somewhere, that when you take the successor, you end up larger than an element of n. Okay? So that was that proof where we said, we know 1 is in there, and if all successors were in there, we'd have all naturals. But we know we don't have all naturals, so there must be 1 in there where the condition m successor less than or equal to all elements of n fails. Which means there must be 1 where you take the successor and you end up being larger than an element from n.
M1 and N1 is that one number in the set.
Yep.
Okay.
Yep, exactly. Okay? So now what did we do? We said we have this thing where m successor is larger than n1. We proved that such a number has to exist, right? It's 6. Yep, exactly. Yeah, yep. So this n1, it's the number where this condition is met, where we said we know there's going to be an m successor that's going to be larger than one of the n's. N1 is that n, where the m successor gets bumped past it. Okay? So once we have that, we then have to say, what's the nature of this m? And that's what this is all about. We say, m, by definition, it's in the list of numbers that are smaller than or equal to, right? So m is somewhere in this list. So we know that this condition holds, because that's the definition of capital M. It's all numbers where they're smaller than all natural numbers in n. But that means that one of these two hold, right? M is less than n1 or m is equal to n1. So what do? We say, let's consider this case right here. Maybe m is smaller than n1. We go through, and if that's the case, we get m plus 1 must be greater than m plus u. And that's nonsense, because u is always going to be at least 1. So that says that this case is out, right? What that says is that m has to be n1, meaning m has to be the smallest item in the list n. We haven't proved that just yet, but we're sort of almost to that conclusion. The largest number here is going to end up being the smallest number here. Okay? So how do we finally prove that? Well, we say, recall the definition of m. M have to be smaller than or equal to all the n's. Well, guess what? We found that n1 was equal to m. So by a little substitution, we find that n1 has to be smaller than or equal to all n's. And that means that n had a least element. It's called n1. I'm sorry. That's just too pretty. It's just, I mean, this picture says it all, right? You've got a random list of natural numbers, and you just start counting. And when you hit the point where an element from m hits an element from n, you've reached the lowest number. That's all the proof says. It says that's guaranteed to happen. Start counting, and when you find an element from m that matches with n, that's the least element in n.
M1 was the small m, like Mary 1 was the smallest item in the list, and N1 is the least element in the list?
N1 is the least element in n. We don't have an M1.
Oh.
We only have an N1.
Oh, I thought we had an M1 also.
Yeah, no, what we did is we said, let M be the element where it's greater than that special N1 thing. Yeah, so we don't have an M1.
Okay.
Anyway, so just a real quick note before we go on, or before we leave, rather. This seems obvious, right? Pick up a list of natural numbers, there's going to be a smallest one, right? Sounds obvious, but it actually fails in some surprising places. The real number line, it actually does not have least elements, right? If you pick up a set on the real number line, let's look at this, say 3 to 7, all these numbers here, with an open interval, which means these endpoints are not included, okay? There isn't a least item here, right? Because say that you pick up this number 4, you can always go smaller than 4, right? You could go to 3.5. But you can always go smaller than that. You could go 3.25 and 3.1 and 3.05. You can always go smaller and smaller and smaller and smaller. And so even in very familiar places, it's not always guaranteed that you're going to have a least element. And so this, setting in the natural numbers, it has that very nice feature that it's guaranteed. In any list, you can always pick out a smallest one. So anyway.